Hey everybody, we are back for video 2 of NMR. So, a couple of things before we get started. Number one, my daughter has told me that she much prefers this color of on my Microsoft whiteboard. This is called Cosmic. She thinks it's much better than the red. So, just as an experiment, I'm going to do this one all in Cosmic and see if it's more festive or fun. If you have an opinion on the type of ink I should use, the color, leave it in the comments. Yes, that's how bored I am right now in quarantine, trying to come up with interesting, controversial discussions. Also, because I am bored and quite possibly going insane, occasionally in my videos I will be putting in some Tiger King references. I have seen the whole series and I am obsessed with it. So, sort of treat them like little Easter eggs. See if you can find any Tiger King references that I make in future videos. Alright, so let's go, all you cool cats and kittens. Let's dive into some more NMR. Alright, so in this video what I want to talk about is the first aspect of what we looked at when we want to analyze an NMR spectrum, and that is the number of signals. Alright? Quite simply, by looking at the number of signals that you might have within a given spectrum, that can tell you how many unique types of hydrogen you have. Now, it doesn't tell you exactly how many individual hydrogens you have. It just tells you how many unique ones you have. Ones that are not the same, not chemically equivalent to other H's. And we've seen this before, right? We've seen in certain molecules, due to symmetry, for example, you can have H's that basically are the same type of protons that you would find on the other side. Excuse me. Alright, so let's take a look. Alright, well, we can start off with, the simplest of organic molecules. We can start off with good old methane. Alright, so I'm going to draw methane. Alright, if I draw methane, it's good old CH4. Right, you can see it's got 4 individual hydrogens, right? However, you can ask yourself, are these all unique types of hydrogens, or are they not? The answer to that, within any example, is to look at the environment that the H sees. So picture yourself becoming the hydrogen. It's very much a visualization exercise here. You become the hydrogen, and you see what is in your environment. If I were this hydrogen, for example, I could look and see, well, I'm attached to a carbon with 3 other hydrogens. Okay? Then I could put myself in the shoes of maybe this hydrogen over here, and I could say, well, I look and see I'm a hydrogen that's attached to a carbon with 3 other hydrogens, right? These two see the exact same environment. You could do the same thing with the other 2 hydrogens, and you would see that they would see the same exact environment. It's literally like walking out your front door, standing in front of your front door, looking around and seeing what you can see. Right, so all of these would be exactly the same. So what we can typically do when identifying different groups of hydrogens is we typically sort of give them group letters, group assignments. So we could say that these were all in group A, right? Okay, so you only have one unique set, so that means on an NMR spectrum, you would only see one signal. Okay? Pretty easy to identify that with methane, right? Well, let's take a look at another one. Let's make it a little bit bigger. Let's say we had ethane. So this one's a little bit different because now you can see that we have H's that are on 2 different atoms. We have 3 H's on the left carbon atom and 3 H's on the right carbon atom, right? So a lot of people will mistakenly assume that, okay, H's that are on the same carbon are identical to each other, but they are different from H's that are on another carbon. That is not always going to be the case. If we wanted to compare, let's just make an assumption. Let's assume that all three of these are the same. Okay? We can assume that all, to each other, we can assume that all three of these are the same as each other. Are these two groups of three unique from each other to make two signals? Well, put yourself in the shoes of a hydrogen again. All right? I want to put a square around this one. You can say, well, this hydrogen is attached to a carbon that has two H's and is also attached to a CH3. All right? Well, you could circle this one, for example, and you could say, well, that is an H that is attached to a carbon with two H's and is also attached to a CH3, right? So once again, you see these two groups, they see the same chemical environment, right? So there's absolutely no difference here between them. So this one would also give you one signal. An easy way to identify this is to find a line of symmetry, right? You can definitely find a line of symmetry right there. So that means whatever is on this side is corresponding to whatever's on that side. All right? All right, let's try another one. I'm going to take that same one. I'm going to tweak it just a little bit. I'm going to replace one of the H's with a bromine. All right, and this is going to change things a bit. All right, again, you can safely assume, I think, that these H's are all going to be identical to each other. I think you can assume that these two H's will be identical to each other. Now we need to see, are the two groups of H's identical to each other or different? Well, if you look at this one, we'll just use a representative H on the CH3. That H goes and sees, that it's attached to a CH2, attached to a CH2Br. This one, however, is attached directly to a CH that's attached to a CH3 and a Br, right? So they're attached to two different things. They see different environments. Also, you can say, well, the H's in this group over here are closer to the Br than the H's over here, right? So they don't see the exact same environments. So what we would say is that these are actually within different groups. You have hydrogens in group A, hydrogens in group B, and that means for one like this, you're going to see two signals. Okay? Still kind of weird, right? Because, as I'm doing these, I'm still in my regular teacher mode from all these years. So I'm saying, okay, I want to say, okay, does anybody have any questions? And then, of course, I'm going to sit here and pause like an idiot because nobody's here. I feel like Dora asking questions to the viewers. But if you do have any questions, please feel free to let me know. It's also kind of sad because with NMR, I usually do bring like a big pack of Hershey's Kisses in and give them out for right answers, but you don't get to do that. However, if you get the answer right at home, treat yourself to a Hershey's Kiss. I think you deserve it. All right. Anywho, let's take a look at another one. All right. We can see, again, here I'm going to draw two different structures. In fact, I'm going to start going into skeletal structure now. We're not going to draw all these bonds and all these atoms out for each one. That would be really, really tedious. I think you guys can move on. All right. I'm going to draw a couple of them that are fairly close to each other, but different enough that it makes a pretty big difference in what you actually see as far as signals. All right, in the top one, right, we have basically two butanol. We have CH3, CH2, CH, CH3, and then we have an H on the oxygen, right? So if we look at this, I think we can say we have a unique set of hydrogens on this carbon. We have a unique set on this carbon. We have one individual one over here that is on the group on this one. A group of three here that's unique, and then a group over here, this one. And if you look at all these, each one of the groups I've circled, if you get in the position of the hydrogen and try to see what your environment is, I think you can safely say that each one of these 5 groups would see a different environment. They would have different neighbors. So this one, we can see, would definitely produce a more complex signal, right? Complex spectrum, excuse me. This one would have 5 signals. Now, the one below, this is just butane. The only difference is I've taken the OH off. So you might think, okay, just removing the OH group, that takes away group E, so maybe we would have 4. All right, we do have groups of H's still on each of the 4 carbons, right? But, you ask yourself, again, are these truly seeing different environments, or are there any duplicates, right? We can see we have a line of symmetry through here. And I think if you go through and do the analysis, you would say that these 2 groups right there, those 2 CH3 groups, they are going to be identical to each other. They're going to see the same environment as each other. And the ones in the middle will see the same environment as each other, right? So in this case, you would just have 2 signals. All right. Hopefully you guys are getting the hang of this. This is actually pretty simple. This is one of the simpler parts of NMR once you get the hang of it. Just like learning how to feed a little tiger cub. It's kind of intimidating at first, but then it just seems natural as anything. All right, let's try a couple of other ones. You can also extend these. Whoops, that looked pretty bad. You can have, molecules. That looks kind of ugly, but it'll do. You can have molecules that have heteroatoms in the middle, like an oxygen or nitrogen, kind of separating things. But you see the same basic analysis, right? This is diisopropyl ether. And if we look at this definitely does have a line of symmetry, right? It goes right through that oxygen. Wow, that looked really bad. Okay, sorry about that. Some excitement in there to get your attention. All right, so we do have 2 identical halves here, and if we're looking at the places where we do have H's, we have them there, we got one there, we got one there, here, here, and here. All right. So again, this would be a case where I think if you looked at the individual H's, you could see that you have a group here that's unique to the one in the middle, right? These 2, A and B, are definitely unique from each other. Within this left side, I think you can also see that the H's on this methyl group are really no different than the H's on this one, right over here. Okay? So within this side here, you only have 2 signals. Over on the right side, again, well, you can see that, the H's of these methyl groups really aren't any different from each other or from the methyl groups on the other side. So these also would go into group A. And the one in the middle here, this one is exactly the way the one in group B would appear on the other side, right? So we can see a case here where symmetry, even though you have several individual groups of hydrogens, really reduces the number of signals that you see because you have a lot of equivalency. So this one would give you 2 signals. All right? Let's try another one. All right. This one's similar, but it's a little bit different because in this case, we actually cannot draw a line of symmetry through the O, right? So this one's going to mean that we're probably going to have a few more unique signals. You know, I could say we have groups of hydrogen here, 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 and here. There's not one at that middle carbon there because that carbon has 4 bonds already. It doesn't have any H's. All right. Now, looking at these, if I am looking for possible points of equivalence, I think I can safely say that these 3 methyl groups over here on the right side, if you look at their individual environments, they're all going to be the same as each other. So I'm going to call, whoops, that's an ugly looking A. Sorry about that. I'll call these group A. And then these points on the other side, these H's, these are quite unique. They're not the same as each other, and they're definitely not the same as what we see in group A. So this one, I believe, would have 3 signals. All right. We have one like this. Whoops. Sorry. All right. This is another one where I think we can see symmetry come into play, right? We have a nice little line of symmetry we can draw right down the middle. So we have individual H's here, 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 and here. And don't forget the H attached to the nitrogen. A lot of people forget to include H's that are attached to like oxygen or nitrogen. Those still count, so don't forget about them. All right. I think it's pretty safe to say that this one in the middle is quite unique, right? Definitely not like any of the other ones, so that's going to be its own group. And then we see the symmetry of the molecule here, so I would say, these 2 methyl groups would be identical to each other. These 2 CH2 groups would be identical to each other, and these 2 would be identical to each other as well. Okay. Whoops, I put 2 A's in here. Sorry about that. How embarrassing. Because I was thinking about that damn Carol Baskin is distracting me. Sorry. All right, so we'll just call this one D instead. All right, so that one would have 4 signals. All right. Hopefully you've gotten a pretty good idea now of how to look at just regular chain molecules and sort of figure out, which ones are going to be unique, which ones are going to be identical, and use that to figure out the number of signals. All right, I'm going to show you a couple of different little quirks here that can be not so intuitive at the beginning, but once we explain them, hopefully you'll understand where they come from. All right, let's take a look at alkenes. All right. Now these are different from the ones that we've been doing because obviously these all contain carbon-carbon double bonds. So let's see exactly how that changes things. Well, first of all, let's just do the very simplest alkene. We'll do ethene. All right. Now ethene is basically CH2CH2. If you were wanting to draw out all the H's, I can. Here they are. I don't know why I drew that line that way. That was dumb. Okay. Now in this case, I think it's pretty safe to say that no matter which H you're talking about, they're all seeing the same environment, right? So these are all going to be in one big group, and of course you would only see 1 signal. All right. Let's tweak it just a little bit though. Let's say I replaced one of those H's with a Br. All right. So now I think it's pretty obvious, right, that this H is in a very unique environment as opposed to the other ones, right? This one is definitely closer to the Br. It's on the same carbon as the Br, right? So it's definitely going to be its own individual group. And so then, you could assume that the other 2 carbons, the other 2 H's, might be the same, right? So then you would say 2 signals. But if you did so, you would be wrong. Haha, bazinga. Yeah. this is going to be the first case where you've seen that two H's that are on the same carbon are not necessarily the same type. And in fact, in this case, we can say that definitely this carbon, this H, is individual and unique from this one. So this one would actually give you 3 signals. Why is that the case? All right, well, let's look back a little bit and see. Let me show you this one. All right, in this case, obviously, these 3 H's are exactly the same. Right? The reason for this is that you get, remember, whenever you have single bonds in an organic molecule, you get constant rotation around those single bonds. Right? They spin much like the blades of a helicopter on the rotor. Right? If a helicopter is at rest, you can see like maybe 3 individual blades sitting there. But once it's running and they're all spinning around, it goes so fast that you can't really distinguish them. Right? You just see one big blur, and that's what the NMR sees here. Whenever these 3 H's are spinning around that single bond, the machine, they go so fast, the machine can't detect any differences between the two at any given time, so it just detects them as one big group, one big blur. However, whenever you have a carbon-carbon double bond, remember, there is no free rotation around that double bond. So the positions of those atoms and groups are locked into place. All right, so if you look at hydrogen B, right, let's compare hydrogen B and hydrogen C and what they see in their environment. And let's use the Br as sort of a touchstone here, right? I think you can pretty safely say that as they're drawn here, hydrogen B is a little further away from the Br than hydrogen C is. Conversely, you can say that hydrogen C is a little further away from hydrogen A than hydrogen B is, right? So they're not seeing the same exact environment. They are unique, they are individual, and that means they're going to appear as different signals. So this one would have 3 individual signals. All right? Let's try another one. I could change it up a little bit. Again. Okay. Now if we look at this one, right, obviously we have 2 hydrogens here and here. They're locked into place, right? But take a look at what they're seeing. This H over here on the right-hand side, is attached to the same carbon as a Br, so it looks across and just a little bit of a distance away it sees a Br. It looks all the way over here to the left-hand side and sees the other Br in the same position. And if you compare the relative position of the H on the left, you'll see it sees the same exact thing as the one on the right. So in this case, these H's would be identical. Okay? However, if we have something like this, I'm going to make this a little bit bigger now. Start moving into some bigger molecules. Let's say we had this. Okay? All right, so we have an ethyl and a methyl group on the carbon on the right. And then we're going to put 2 H's over here. Let's see if we can count the number of H's. All right? Whoops. What the heck did I just do? Sorry about that. Okay, so let's first go ahead and circle all the H's here. So we have an H here, an H here. We have a group of H's here, a group of H's here, and a group of H's here. All right? Okay, so I think it's pretty safe to say that the ones we have circled over on the right-hand side are all going to be quite unique. There's not going to be any other group. They're not the same as each other. They're not the same as the H's on the left. So these are definitely 3 unique signals. All right? All right, if we look at the 2 H's on the left-hand side, right, the one on top, if we want to compare, the one on top is probably going to be further away from signal C, or the signal C, than the one on the bottom is, right? They are locked into place. The H on the bottom is going to be further away from signal A than the top H is, right? So again, these two guys are not seeing the same thing. So you would have 5 unique groups of hydrogens, and you would have 5 unique signals. All right. One more with alkenes. Dang it. All right. So take a look at this one. All right. Pause it for a minute. See if you can, figure out the number of signals yourself. All right. Now, again, I'm going through this, and I'm going to see there's an H there, there's an H there. They may or may not be the same. We'll figure it out. But we definitely have, that. We have an H here. We have an H, group of H's there. We have H's there. Here, here, and here. Again, the central carbon in the middle does not have any H's. All right. Okay, so what I can see here is I think all of these methyl H's, right, they're going to see the same exact environment as each other, right? There's going to be definitely a bit of symmetry in this tert-butyl group. So these guys are all going to be equivalent. We'll call those A. All right. This is a unique group over here. That's B. This is a unique group. This one's unique. And again, I think we can see here that the individual H's that are on the double bonded carbon, they definitely see different groups. The top H, for instance, is closer to the Br than the bottom H is. So E and F. So this one's going to have 6 signals. Okay? All right. So with alkenes, again, remember, you have to look a little bit more closely at the H's that are on double bonded carbons and whether they're equivalent or not, because they are locked into place. There is no free rotation. Okay? All right, one more classification I want to look at, and that's cyclic. We haven't done anything with rings yet, so let's see what happens whenever we have cyclic H's. All right? So again, let's just work with cyclopropane. Now, cyclopropane looks like this. Yeah, that looked ugly. Oh, sorry, that drawing was uglier than a bleached mullet. All right. Oh, God. Sorry about that. There we go. Okay, so if you look here, we have 6 hydrogens within this, and this is a highly symmetrical molecule, and I think it's pretty easy to see that all of these H's are the same. They have the same environment, so that's just going to be 1 signal. All right. Well, let's tweak it a little bit. Let's put a bromine. Okay. So if you put a bromine on there, and then if we want to draw out all the rest of the H's. That was kind of gross. Sorry. But it'll do. All right. So if we're looking at this, we can see, definitely one here that's unique, right? And then, these over here and these over here, these appear to see the same environment as well, right? So this one appears to have 2 signals. However, this is another one where this is wrong. This one does not have 2 signals. This one actually has 3 signals. Now, how is that possible? Looking at this diagram, looking at the structure that I have here, it does appear to only have 2 signals. However, This is because we're forgetting something very important about cyclic molecules. Much like with alkenes, if you have a ring, we have no rotation around single bonds. We're not going to have any rotation around single bonds that are locked in the ring. So that means the individual components that are coming off of the rings, they are locked into place, right? And if they're on a ring, really there's one of two places they can be. They can be on the top side of the ring, or they can be on the bottom side of the ring. All right, so this changes things a little bit. Those types of structure drawings are not sufficient to really judge what's going on. So for cyclic materials, really the best type of structure to draw is something that's going to be probably a bit new to you. It's called a Haworth projection. You may have seen these before, but kind of doubtful. These are used a lot in biochemistry, so if you take biochem next year, you'll probably see some. Basically, what you do in a Haworth projection is you take a ring, and it's almost like you can hold the ring in your hand, and you're sort of flipping it at an angle, almost like you're looking at it sort of from the side, sort of from the edge, right? So, for example, if we took that triangle in cyclopropane, it's kind of like we're taking it, we're picking it up, and we're sort of looking at it from an angle. And so what I'm going to do is I'm going to shade this in to sort of indicate the fact that we're looking at it from an angle. And what we do is we draw the bonds going straight up or straight down from the plane of the ring. Okay? I'm going to erase this to give me a little bit more room. All right. So in this case, you can see all 6 individual bonds, 3 of them coming off one side of the ring towards the top, the other 3 going towards the bottom. All right, and so we said one of the carbons had a Br. I'll just put that right there, and an H. The other 2 carbons each had 2 H's, so I'll draw those there, and I'll draw those there. Okay? So now let's see if we can figure out how many individual types of hydrogen we have. All right? I think it's pretty safe to say that this one is quite unique unto itself. It's the only one attached to the carbon that has the Br, so this one, we'll just call this one A. All right? Now, the assumption was that this hydrogen and this hydrogen over here, originally we thought, okay, those are going to be the same. They're going to be equivalent to each other. However, you see this is actually not the case. The top H is actually much closer to that Br than the bottom H here. The reason being, all of these components are locked into place because of the ring, so this Br is always here on this particular side. All right, so for that reason, I think we can say that these 2 H's are definitely different from each other, so I'm going to call one of them B, one of them C. All right, now if we look at the other H's over here, right, I think this one over here is going to see the exact same environment that hydrogen B sees. It is it's on the same side of the ring as the Br. It's attached to a carbon that has another H, right? Sees the exact same environment. So this hydrogen is going to belong in group B, and the one down below, this one's going to see the same environment as group C. So that is the reason that this one has 3 signals. Okay? All right. Let's try, you could try several of these. We could try this one. Whoops. Put a little dash wedge notation in there. This one's got 2 BRs. All right, and obviously if the BRs are both on wedges, that means the BRs have to be on the same side of the ring. All right, so what we would want to do is draw a Haworth. All right, we draw our 6 bonds. All right, we know we have 2 BRs. We know they're on consecutive carbons, and we know that they're on the same side of the ring. So this would be one particular representation. And then everything else would be filled in with H's. Okay? So if we're looking at this, I think definitely this one and this one would be the same. This one would be unique. It's definitely much closer to the BRs than this one is. So again, I think this one would have 3 signals. Again, I can't stress it enough. It's all about the environment that the individual H's or groups of H's see. All right, let's try one more. Let's do this with a trans. Yeah, sorry. So this is basically the same thing, except we have BRs located trans to each other instead of cis. All right, so again, BRs on consecutive carbons, but this time they're on opposite sides of the ring, and everything else is filled in. All right, so in this case, I think that if we look at this one, it's attached to a carbon with a BR, and it looks across and it sees an H on the other side. This one's attached to carbon with a BR, sees an H on the other side. This one sees the exact same environment as the top one, so I'm going to say that these two are going to be identical to each other. All right, and these two are also going to be definitely identical to each other, seeing the same environment. Okay. All right, so I'm going to stop right there. Work through this video, work through some of these examples. Feel free to make use of that pause button. And again, be working some of the examples in your book too. They give some good practice problems throughout the chapter that can help you with this. All right, until next time, hope you guys have a good day.